Hello again. My name's Don. I'm hosting this webinar on behalf of the UKAN Plus NDE SIG. Our speaker today is Dr. Andrea Iglesias from Penn State University. Just so that everyone knows, this presentation was recorded and will be available on the UKAN Plus YouTube channel. Andrea, over to you.
Awesome. Thank you, Don. So I'm very excited to be here. I'm honored by the invitation, and I hope that I can show you some of what we're doing in my group and some of the bounds we're trying to cross in the context of how we use ultrasound for characterization. So with that, I'll just get started. So like Don said, my name is Andrea Arguelles. I'm an assistant professor and associate head for diversity and inclusion in the Department of Engineering, Science, and Mechanics at Penn State. Our group has mostly focused on characterization of microstructure, and I'm going to talk about a couple projects in which we've been doing that. So why do we want to do any of this, or why do we care about ultrasonic characterization? So the key motivation is that uncertainty in part quality is limiting the application and implementation of various advanced manufacturing processes. The most common scenario that we see this in is in 3D printing or additive manufacturing of metals. So the image that I'm showing you right here, I like to show this image because it shows that it's not only about the presence of flaws or features. I'm hesitant to call them flaws because sometimes these things can be by design, but it's not only the presence of the features, but also the type of features that you have. So for example, something like round porosity that you see in the very first figure is going to affect the response of your material quite differently from something like the figure on the third panel, where the damage is a little bit more localized, and that's going to access the stress concentrator differently from a distributed porosity like this. When we think about the way that characterization is usually handled, we're generally dealing with processes that require pretty extensive sample preparation. So when we think about things like microscopy or whether it's electron scanning microscopy or optical microscopy, you need to section the sample and prepare the surface sufficiently well to be able to get the information that you need. So for example, in the image that you see here, you can get the orientations of the grains based on electron backscatter diffraction, but this requires that you look at a very specific portion of your sample and then extrapolate the behavior that you're seeing in that very small portion to the rest of the sample. As you can imagine, when we're dealing with advanced manufacturing processes, that extrapolation is not necessarily all that accurate. So you can have properties or features in one particular section of a sample that then when you move to a different location are not necessarily going to translate. And that's essentially the problem that we're trying to address. So in my group, our research is using ultrasound for the non-destructive characterization of materials. And the way I like to frame this is that we do it at multiple length scales. So we're not necessarily saying that we're going to be able to get the level of precision in imaging that you would get from some of the conventional techniques, but you'd be able to map it over a larger surface so that then you can do subsequent inspection with some of those methods to obtain the information that you need. And then the second thing is that we try to do this at various stages of the manufacturing processes, which I'm going to elaborate on the following slide. And we do this through an integrated experimental and modeling approach. My training is all on the analytical mechanics-based modeling of scattering in polycrystalline media. So a lot of what we do is implementing some of these mechanics-based models to understand the experimental results that we're getting and hopefully obtain more quantitative information about the structure of the materials that we're dealing with. So I said I would talk a little bit more about what I meant by various stages of the manufacturing process. This is essentially how we like to graphically represent this. One of the ways that you can think of ultrasound, and I'm sure that a lot of you in this group probably have awareness of this, is kind of in that conventional NDE sense. So we have that post-process inspection of ready for service components. There are challenges associated with this post-process inspection, particularly when we're dealing with parts that are more complicated in geometry, because conventional techniques are not necessarily set up to be directly used there. So we have some work in collaboration with the University of Cincinnati on improving these processes through cryo ultrasound. That's beyond the scope of what I'm going to talk about today, but it's important kind of in the bigger context of what we do in my group that you understand that that's one component of it. And then the last panel that you see right here is essentially the complete opposite end of the spectrum. So if we, at first we're talking about post-process inspection. So essentially the part was designed, manufactured, and it's ready for service, and you're just doing that final step to check that it doesn't have any critical flaws. The one on the very end is, what if we start considering this at the design stage? So we have some ongoing collaborations with faculty in the School of Engineering Design here at Penn State, where essentially we're trying to say, what if the designer knew that in designing that complex shape that they're very interested in making, they also need to consider inspectability? Because even if the design is optimized for all of these various different features, it doesn't really matter if you can't put it in service, because you can't certify that it's going to pass the requirements for a safety critical application. So we have a little bit going on both of those ends of the spectrum. But the one that I'm going to focus on today is, how do we use ultrasound in the development of process structure property relationships? So essentially, as I was mentioning before, in a lot of the structure characterization that we do in just in the conventional development and manufacturing processes, we're relying on this very time and resource intensive process of having to break samples open and understanding what that internal structure is. So essentially what we're trying to do in my group is instead implement ultrasound as a technique that you can use to understand those internal structures, understand ultimately the performance of the parts, and then figure out how to modify the process to obtain an optimized version of the parts that you're trying to make. I'm going to talk about this in the context of two different manufacturing processes. So the first one is the cold sintering process, and the second one I'm going to talk about is binder jet printing. So the cold sintering process, as the name would suggest, is a sintering procedure, and this is going to be focused on ceramic parts. And then for binder jet printing, this is a 3D printing application, which for that portion of the presentation, we're going to focus on metal, stainless steel, specifically parts. So how do we actually use ultrasound to understand this? So in the, again, conventional NDE sense, we're dealing with the direct reflection of ultrasonic waves by an object in the material. So we're dealing with diffraction limited imaging, where you essentially need flaws that are at least half that wavelength in order to get a reflection from the flaw, which is fine. We do use some of that information for some of the parts, because even though the process should be optimized to not obtain flaws that are that large, the reality is that sometimes in the responses that we're getting, we're seeing that that is still happening. So we're getting direct reflections from some of the features that are coming up in the part, which I'll talk about particularly in the cold sintering components a little bit more when we get to it. But really what my group is focused on is, how do we use some other ultrasonic parameters to get more quantitative information about the microstructural features? Now, this is where we kind of have a little bit of a trade-off. So what do we have to give up in order to get information that is at a smaller scale? And in our case, what we choose to give up is the ability to directly image. So essentially what we're dealing with is we're propagating waves through a finite volume and then obtaining statistically relevant information about the microstructure in that volume. So if you think, for example, of a columnated beam from just a piston transducer, we're essentially saying, in that cylinder that you're inspecting with that transducer, what information can I gather through quantitative parameters? The ones that I'm going to show you today are kind of in that the first round of characterization that we can do, and that is wave speed and attenuation. So just as a crash course for that, we know that wave speed is going to be related to those effective properties of the medium that the wave is propagating in. So in our case, we're not going to relate wave speed to something like porosity. So we know that there is an inverse relationship between these two parameters. So how do we get this information and then combine it with some of those mechanics-based models I talked about before to obtain quantitative information about the porosity in the parts? And then second, we have attenuation, where although it's also dependent on those effective properties of the medium, the main use that we are applying this for is actually the characterization of scatters that are smaller than that half wavelength limitation we talked about before. So essentially we're dealing with, so we know that although I'm not getting a direct reflection from the feature that is in this propagation path, I know that my wave is going to lose more energy as it propagates through a volume where there are localized features that wouldn't necessarily affect the wave speed directly, but that are definitely impacting the scattering and the absorption of that wave as it propagates through. So with that background in mind, know that for the work I'm going to be presenting today, all of the tests were conducted in an immersion ultrasound setup. The samples were immersed in water for the most part. I don't think I'm presenting on any samples that needed a different coupling medium. I think they were all pretty stable in water. And the other thing is that we used a thickness independent method for the inspection. And this was critical because we knew that there were small variations in the thickness of the parts that needed to be corrected for in order to ensure that the mapping we were doing over space of these ultrasonic properties was actually representative of changes in the internal structure, and that we weren't just capturing some of these thickness variations that are inherent with the manufacturing process. So essentially, we just took the samples, we raster scanned them, and then we obtained quantitative information at every single point. So a whole A scan at every single point that then we could post-process and obtain quantitative information about the wave speed and attenuation for the two different sample sets that I will be discussing. All right. So first, I'm going to talk about the project that has to do with the cold sintering process. So the results that I'm going to be presenting here today were all collected and analyzed primarily by my PhD student, Haley Jones, and my previous master's student, Elizabeth Trotman. And this is all done in collaboration with Professor Susan Troyer-McKinstry in the Department of Material Science and Engineering here at Penn State. So I assume for most of you, cold sintering is probably not something you're nearly as familiar with as you are with ultrasound. So I thought it was important to start with a little bit of a crash course on what I mean by cold sintering. So cold sintering, like other sintering processes, is essentially just a process to apply pressure to bring particles together and solidify into a material. The main difference is that if you think about the sintering of a ceramic, more than likely you would have to deal with temperatures in the 1,000 degrees Celsius range and pretty high pressures. And in the cold sintering process, the objective is to bring these temperatures down significantly, hence the name, so that we can reduce the energy resources that are needed to sinter these materials. But also, more importantly, we can also now combine different material types that were not compatible in a high temperature sintering process. So in cold sintering, the process looks something like this. So you have a powder that you mix with a transient liquid phase. That transient liquid phase is the one that is assisting in the densification of the powders once you apply the uniaxial pressure, but still staying, again, like an order of magnitude lower in the temperatures that we need. And at the end, you have a densified solid with hopefully the desired microstructure, and we can achieve many compositions. So that's all fine. But what is the challenge when we're using the cold sintering process? So the main challenge here is that we have macro and micro flaws that arise and deteriorate the mechanical and functional properties of these materials. So what I'm citing here is a couple of different things. So first, let's talk about the picture in the background. So the picture in the background is a cold sinter part that had a 95% relative density. So this is pretty much the standard for what we use to qualify a part as good or bad when it comes to these kind of sintering processes where you're just creating and generating a bunch of pieces. But you see that even though it had a 95% relative density, which is considered actually quite good for ceramics. I know for those of you that work in metals, that's probably like, no, that sounds quite low. 95% is actually quite reasonable. But when we look at the properties, the sample actually broke quite easily just in our hands. Now, this is also reflected in the literature when you look at the characteristic strength of parts that were cold sintered versus conventionally sintered, and you can see that that characteristic strength drops quite significantly, as does the Weibull modulus, so we have more of that variation, which is not exactly desirable. Now, as I mentioned before, the standard is to use relative density of measurements, and as you can see from the example in the back, and from some more in-depth data that we've collected, that's not necessarily reliable. So what we wanted to do was say, okay, so if we create a set of samples that has some range of relative density, how does that compare in the context of their ultrasonic properties? And is that more representative of the mechanical and functional properties that we're getting for the parts? So what we did is we took 2 sets of cold sinter zinc oxide samples, and the main difference here was that we dealt with 2 different transient phases. So that liquid phase that I talked about that facilitates sintering, I'm going to come back to that because it turns out that that transient phase is actually critically important, and that ultrasound allowed us to identify some of the ways in which it affects that final part. So we did 2 sets of that, and you see that we have a range in the relative densities that goes from that 80 to that 97% range. In order to obtain that range in relative densities, we needed to change things like the pressure, the temperature, and the sintering time. And then the final thing that we played a little bit around with, because of what ultrasound enabled us to characterize, was the heating rate. So then that brings us to some of the ultrasonic results and what we learned from doing this type of analysis. So the first thing we did was just look at the wave speed. Again, it's a pretty simple metric we could start with. We were collecting full A scans at every location, and we could do just a cross correlation and get a quantitative measure of the wave speed. Again, thickness independent based on the type of measurements that we were collecting. And when we did that, part of it was exactly what we expected. As you increase the relative density of the bulk part, the average wave speed in the samples increased, right? So you can see that the range here goes from 4,100 to 4,500, and then it goes then all the way up to 5,000 to 5,400. So they each have a 400 meter per second range, but that mean value is slowly increasing as we increase that relative density. Again, that is pretty expected, but there were a couple of things of note when we started looking at the ultrasonic results. The first one was that you see that there are spatial inhomogeneities in the wave speed. So even within a single sample, so again, all of these have the exact same range. So when we look at the 84%, there is a lack of total uniformity in the wave speed for the whole sample. This reflects the fact that ultrasound allows us to now spatially map how the sample is actually densifying through the sintering process, rather than just getting a bulk value that represents the whole piece. So in doing this, we were able to also identify some of the things that were happening in terms of the evenness of the pressure that was applied on the parts, and the evenness of the temperature distribution of the part, as well as that liquid phase distribution. So this already kind of gave us some of that information. The other thing of note, though, was that even though we were getting fairly high relative density, so for this last sample over here, and by the way, these are all zinc acetate samples, you see that for the 96% dense sample, we still, 5,400 was way below that theoretical wave speed for a fully dense zinc oxide material. So that already started sparking some conversation about what could actually be causing the difference between these. And the other thing that we noticed is that because we were using geometric relative density values, a lot of times we were missing the fact that for some of the larger samples, there were actually large eliminations that we get direct reflections from. So as I said before, this is already quite informative in the context of what was happening in the sintering process and some of the changes and modifications that we could make to the processing so that we could obtain more uniform samples. So that's exactly what we did when we moved on to do formic acid instead of zinc acetate for that transient liquid phase. And what you see here, so again, the range is a little bit larger here for these samples at 600, but you see that there's much more significant uniformity in the samples. We don't have the large laminations that we were seeing before. So again, by characterizing the samples with ultrasound, we were able to identify some of the pieces that we could put together and ensure that we were getting a more uniform sample. So this was all great in identifying individual samples and their variations, but what we really wanted to do was now understand on average, so some of these average properties, why weren't these samples matching up with what we would expect for a fully dense zinc oxide sample. So what you're going to see in the next couple of slides is that we actually started to look at some micromechanics models to understand the effective elastic modulus of each of these samples relative to the shape of the pores that were within them. So we knew for a fact that there was going to be porosity. We had relative density measurements that reflected that. But what we did not know was whether those pores were fairly spherical and uniform in shape, or if they had some preferential shape that we were perhaps capturing with some of our ultrasonic results. So what you see in this figure is Hessian Streakman bound, so the upper bound for that wave speed and what would fall there. And then what you see in the colored bands is that we actually look at the HLPU regions based on different aspect ratios for the force. So everything that you see in the purple and then in the light blue represents force that are oblate. So that's oblate relative to the pressing direction. It makes sense that if you're doing a pressing process like we were doing in the sintering, that the force would be oblate, or at least that's what we would have expected. And as you move to the green region, we're now getting prolate spherical and then prolate force, so the ones that are elongated along that pressing direction. So now if I bring in the actual data that we collected for these, you see that they fall generally in that oblate region, so in that blue part that you see right here. So in order to confirm that the variations that we were seeing in the wave speed were actually associated with that change in the shape of the force, what we did is we actually conducted X-ray CT in all of the samples that were composing this set. And what you see in the inset diagram over here is a histogram of the pore shapes from that X-ray CT analysis. And the nice thing about this is that this analysis essentially confirmed that a lot of the pores were actually oblate, and the response that we were getting from our ultrasonic data was actually supported by that change in the pores. So this already gave us kind of some initial information on the type of quantitative data that we were able to gather just based on the ultrasonic analysis, and the combination of that with these micromechanics-based models that tell you more about the morphology of the microstructure that we're dealing with. But another thing that was interesting and that we're still in the process of exploring is that once we started looking at the formic acid samples, you see that they no longer quite fall into that oblate pore category. We haven't completed X-ray CT on all of these samples, but we have no strong reason to believe that the formic acid pores are going to be significantly different in shape, although they might. So we think that another contributing factor, as you can see, like these are kind of shifted in that Y direction. Another contributing factor might be that the formic acid samples are actually forming stronger bonds between the grain boundaries. So if we have stronger bonds between the grains, we might essentially be getting a larger effective modulus for the samples that were processed using formic acid. So again, part of what this illustrates is that the samples that were processed with a different liquid phase are going to have different effective properties. And this can help us identify different parameters that we can change in that manufacturing process and understanding how these parts behave. Which then brought us to the analysis of some of our ultrasonic data. So since we had done X-ray CT on all of the samples that were manufactured with zinc acetate as the liquid phase, we were able to do some one-to-one comparison of the features that we were seeing in the X-ray CT and the features that we were seeing in our ultrasonic maps. But I'm sure for those of you that have tried to do this one-to-one analysis, you're probably immediately identifying that there are plenty of features in the CT that are not necessarily being captured in the ultrasound, plenty of features in the ultrasound that are not necessarily showing up in the CT. So we think that it's a combination of a few different things. So the CT data you're seeing here is the sum of the pores through the depth of the sample, so that you can have a one-to-one comparison to the ultrasound. And essentially, it's doing a relatively good job of mapping some of those features, but some of these features were actually rather fine in terms of features that were essentially just capturing flaws along those grain boundaries that, although we're not necessarily imaging them, they're essentially affecting our ultrasonic response in a way that wouldn't show up in the CT. And by looking a little bit closer at that, so for example, at this feature over here, we saw a couple of different things. One of them, this was really interesting to see. So the sample was pretty uniformly porous across the whole volume. And it was actually the highly densified regions that you see kind of in this area over here that were acting as scatterers, or at least that's our presumption for now, that we're seeing highly densified regions acting as scatterers, because the rest of the relatively porous area is homogeneous as far as the ultrasonic wave is concerned. And now we're dealing with a sharp change in that impedance once we get to a region that is essentially 100% dense. And then the other part that we were able to observe is that for the zinc acetate samples, and this supports the argument about a weaker bond between the grains, there was actually some residual liquid phase, so that zinc acetate wasn't fully leaving the system during the sintering process. And again, although we are by no means suggesting that we're able to image things in the 5 nanometer or 100 nanometer range, these measurements allowed us to target specific regions to study further and understand through the use of microscopy exactly what might be happening in those regions. Lastly, one of the things that we wanted to look at in the context of cold sintering was the effect of heating rate. And what you see right here is that by mapping that attenuation, we could pretty efficiently evaluate the effect of that heating rate. In the case of the use of formic acid as a transient liquid phase, we actually saw there was quite a sharp variation in the uniformity of the samples once you went down to a 1 degree Celsius per minute heating rate. And what you see in the dashed line is actually the fracture pattern that we saw for each of the samples. These were all ball and 3-ball mechanical testing. And for those of you that might not be as familiar, essentially the ideal pattern we would be looking for would be something like this. And in the samples that were processed more quickly, we were getting a pretty off-axis pattern of behavior and in the response from the samples. You can see that a little bit more clearly here. So again, these are just the wave speed maps, but you saw the attenuation maps in the previous slide. You can see that even from the fracture patterns and from what's left over and the sample is fracturing, that the mechanical strength wasn't, and in the quantitative value, the mechanical strength of the samples wasn't nearly as good as when we decreased that heating rate. And the use of ultrasound for characterization allowed us to do this a little bit more efficiently. So we didn't have to create a large volume of samples that then we had to test at the different temperatures, but rather a smaller set, but then also to give us some of that information from more conveniently. Both of these studies are all already published. So there's one that focuses on the zinc acetate samples, and then the second one that focuses on the formic acid samples. So I've included QR codes for these here. So I'll leave them up for a second in case you want to take a screenshot of that. We're more than happy to discuss these further with you if you're interested in these results. So this material was all supported by that NSF grant that I listed at the beginning. And you can kind of see in summary kind of some of the variations that we were seeing with the samples. Which then brings us to the second set of experiments that I want to talk about, and those are the binder jet printed samples. So we're switching over to metals and to a 3D printing process. So this work was supported by the 3M company. Most of the results that you're seeing here today were obtained and analyzed by my student Olivia Cook. She's a PhD candidate in my group, and this was all done in collaboration with Alison Beasley in the Department of Engineering, Science, and Mechanics, and her student Nancy Wong. And Chris Kubi was also involved in the analysis of the data that you're seeing in this section. All right, I'm going to take a breather and a sip of water, and then we'll come back to talk about binder jet printing. So for those of you that are maybe not as familiar with additive processes, or particularly with binder jet printing is essentially like a lot of the other powder bed processes where you're laying a layer of powder and additively creating a 3-dimensional shape. The main difference in binder jet versus say something like powder bed fusion, where the powders are fused together using a high intensity or high power laser, is that in binder jet we're using an organic binder that essentially just holds the particles together for now, and then you go through a secondary step of either sintering or infiltrating with a second material to actually bond everything together. So you burn off the binder and then you either, again, infiltrate with a second material or just sinter the part itself. We've done analysis of both infiltrated samples and sintered samples. I'm only focusing on the sintered samples today, and particularly a sintered block of stainless steel 316. Now, I feel like most of you can probably relate to the fact that we wanted to start with the simplest case scenario and just start with a sample that we thought the behavior would be rather simple. We could establish kind of some baseline in the ultrasonic response and then move on in complexity. So we wanted to do just a block that was an inch by an inch, couple inches, so 25 millimeters, and 50. And we just wanted to ultrasonically test that. We were like, this is what the company that provided the samples said was their optimized process. Surely this is going to work smoothly, and these are going to be samples that are going to be rather easy to analyze. But the reality was that once we started doing that testing, we actually got quite low transmission through the center of the samples and much higher transmission around the edges. So this was already kind of suggesting that the samples weren't necessarily as simple as we anticipated. And it ended up being a pretty interesting analysis of what resulted from these samples. So it was all good in the end, but this was kind of our first indication of like, oh, wait, so maybe these samples are not responding the way that the manufacturer thinks they are. Now, to begin with, these were fairly large samples, so they were an inch in height and width. So that didn't necessarily lend itself to very detailed analysis. So what we did is we went ahead and sectioned the samples and then rescanned the samples with our thickness independent method to get wave speed and attenuation on some of those thinner slices. So the samples were sectioned something like this. So you have the printing direction, and then the slices just kind of cut across as we go through the depth of the sample. Now, when we cut up these samples, we kind of expected that porosity was going to be the dominating factor. You know that it's kind of the name of the game when it comes to additive. Porosity seems to be that primary issue. So we just kind of assumed that that would be what dominated the response that we were seeing in these samples. When we look at the attenuation results supported that. So we cut up in the samples. You see that the sample in the middle has higher attenuation. The ones at the edges have lower attenuation. Makes sense. That's all kind of in line with the fact that we're getting low and high transmission in those areas respectively. But then when we look at the wave speed, if porosity was the driving factor, we would have really anticipated that as soon as you're moving away from the edges of the sample and towards the center, that the wave speed would actually immediately drop. And then we would see that relationship to porosity, but that is not really what we were seeing. We were seeing about a 5,800 meter per second wave speed, and then it would jump to about 5,900 before actually dropping to a much lower wave speed in the very, very center of the sample. So we went ahead and did a little bit more quantitative analysis of the porosity at the different interfaces. So we took the samples and actually did optical microscopy and sectioned the different pieces, and sure enough, there was a little bit more porosity right in the center, but going from the edge to the kind of this middle region of the samples wasn't really supporting that porosity was the driving factor in our ultrasonic response. Now, being someone that was trained in scattering and polycrystalline media, obviously our next thought is always to go to grain size, and that's exactly what we did. And what you see was actually rather interesting, and it was particularly interesting in the context of what had been previously reported for binder jet samples. So binder jet samples, kind of one of the advantages that was pretty widely cited was that you would get this uniform sintered structure for the grains, like small grains that were very well developed. But what we saw once we went to the analysis of that microscopy data was that at the very center, you had much, much larger grains that you can see those boundaries in the image on your screen. But essentially, we were going from grains that were like 250 microns in diameter down to grains that were more in the 75 microns in diameter range. So that significant change is actually what was dominating the response that we were seeing with ultrasound. And then the other thing that we noticed that we thought was interesting was that in the center to edge region, the pore structure that we were seeing in the samples was round and isolated. But then once you got to the very center of the sample, now we could only look at this in the 2D plane, at least for now. What we saw was that the pores were pretty irregularly shaped. And this got us wondering how these pores were actually to be represented if you were to look at them in a three-dimensional space. So in order to analyze that further, what we did was we took some tensile specimens from an equivalent block. So this is not the exact same block we had tested before, but it was a block that was created with the exact same conditions. And we took them from different regions that we knew were going to have a little bit of that varying response. So we wanted some in the area where we had really small grains and almost no porosity, some in the area where we had large grains and the pores were in the grains and in the grains and the boundaries, but like rounded and separated. And then some where you had this much more irregularly shaped and mostly concentrated between the grains, and see the response of these and how those varied. So we started by doing X-ray computed tomography in each of those blocks. And what you see right here is that it turns out that the pores that were showing up as irregular in that 2D plane were actually very large interconnected pore networks. So what you're seeing here on the right, each of the pore networks is colored by an individual shade. So everything that you see here in the dark green is actually a pore that connects the whole way through. And it actually went in the thickness of the sample that we were dealing with, which was 1.5 millimeters, the pores actually extended from edge to edge. The chances are that the pore network was actually extending significantly outside of that plane as well. So this was already pretty informative in terms of what was happening in the behavior of these parts. So we went ahead and did our same ultrasonic measurements as before. So thickness independent wave speed and attenuation mapping. And then what you're seeing for the pore reconstructions now is that they're just simply oriented in the plane that the wave is seeing it in. So all of these measurements were longitudinal waves that were normal to the surface. So we essentially just reoriented the maps so that we could one-to-one look at the relationship between that and some of the ultrasonic parameters. The first three samples in terms of mapping are obviously not going to show us anything that interesting because the pores were isolated and small. So sure, you see some variation in this, especially in the wave speed that I'll talk about in a second. But other than that, nothing too interesting. That said, when we move to the samples that had these large pore networks, then you see some spatial correlation in where the pore networks were and the responses that we're seeing both in the wave speed and attenuation. So we wanted to go ahead and make that a little bit more quantitative. In order to do that, we separated our analysis between low and high porosity regions. The way we defined this, just for the purpose of this analysis, was we said anything less than 0.5% by volume is considered a low porosity region. So we separated our data relative to the voxel size that we were able to obtain from the transducers we were using and the spatial resolution of the maps that we collected. And then high porosity areas would be anything where the pore descriptors, where the porosity to that volume was greater than that 0.5%. And then we went ahead and calculated some pore descriptors based on the XCT data that we could then directly correlate to our ultrasonic parameters. Now, what we saw was that the difference in response, and I should have pointed that out here, although we don't see anything too interesting in the mapping, we do see that there's a definite increase in the attenuation and the wave speed when we look at the first three maps. And what we saw in those low porosity regions is that this was all dominated by that change in grain size that we had identified in the larger blocks. So we went ahead and represented Stinky and Kainos unified theories for scattering in polycrystals. So we did the wave speed as a function of that grain diameter. And although the error bars are large expectedly because we have a distribution of those grain sizes, we see that that change in the wave speed that we're seeing across the samples is dominated by that change in the grain diameter. So porosity is not playing as big of a role because we're talking about that less than 5%, and the variations that we're seeing in the grain size are rather significant. Now, if we look at the regions where the porosity was high, we needed to be able to essentially convert our three-dimensional X-ray CT data into a 2D map. So we went with a couple different features that you could look at. So we took a voxel of X-ray CT data and propagated that all the way through the thickness of the sample, since that's essentially what our ultrasound was doing. And we calculated in that little volume, we calculated the pore volume fraction, the average pore volume, and then what we call the projected pore area. So essentially, if we had a pore that was oriented like this, we wanted the area that would actually be perpendicular to that wave propagation direction, since we anticipated that that might have some good correlation to the ultrasonic parameters. Now, keep in mind, we considered a lot of other metrics that are not shown here. So like these were the three that showed us most significant correlation to our ultrasonic results. So in doing that, we did point-to-point correlations, and we saw that both the pore volume fraction, as expected, but also that some of the projected pore area showed pretty decent correlations in a point-by-point basis to the attenuation measurements, which was really good to see, as like it could give us some quantitative information about what was happening in these samples. Now, I think some of the more interesting results are actually on the wave speed side. So one of the things that we saw was that if we were to consider the spread of the wave speed, you see that there's a lot of scatter in this lower region. So essentially, if I were to draw a line just below here, the 6,000, and just consider the data that is falling outside of that, it's not really following much of a quasi-linear trend that you would expect from, say, Mordanaka or a Hashim-Streetman model, right? That's going to give you that quasi-linear relationship between wave speed and pore volume fraction. But what we noticed was that if we were to threshold essentially the wave speed by those values where we knew it was regions where there was highly interconnected porosity, then we see that the slope of the line, once you eliminate this lower data, is actually a lot closer to that Mordanaka estimate in the response. Now, obviously, there are some simplifications in this analysis. The Mordanaka model is still assuming static properties, and so there are inherent assumptions there. But there is reports that the effective modulus in a static problem is going to be more significantly affected if your porosity is interconnected versus if you have porosity that is evenly distributed. So this was kind of exciting to see that we're seeing that reflection in our ultrasonic data as well. Now, this work has been going on a little bit longer, so there are quite a few publications related to this analysis. The results that I showed you today are primarily in this one. So the X-ray computed tomography, this materials characterization paper, and also this additive manufacturing paper is the one that shows you the results on the slices. So we're happy to share any of those with you if you have trouble accessing. But a lot of interesting information was gathered from this data set. So this was all supported by the 3N company. The grant is listed on the slide, but this was all very encouraging in the context of the kind of information that we could extract when you use ultrasound to understand the underlying structure of some of these parts. So with that, I want to thank some of the sponsors of our research. I want to thank my research group. They were the ones that made all this possible. And based on Don's request, like I think it was like a 45-minute, 15-minute situation. So I think we should be right on time for that. I'd be happy to answer any further questions about any of this or any of the projects that I didn't have time to present. Thank you.
Amazing. Thank you, Andrea. Do we have any questions from the room? I've probably got one just to start. I like the two different types of data you presented, right? And the methodology was the same that you'd apply for the kind of two different materials. What defines your spatial resolution? Because I can see that it's a small step size, but is it based on the transducer then?
Yeah, that's a great question. So I didn't give you a ton of details on the frequencies we were using. So we generally try to keep our spatial resolution to about half of the spot size of the transducer. So there is definitely, not every point is independent. There is overlap because of the spot size of that transducer, which is dependent on that frequency. So yes, it is transducer dependent. We just keep the scanning resolution a little bit lower than that to get some overlap. That's why the data also looks a little bit smoother on the ultrasound side, because the points are not truly independent. Yeah.
Okay. And I think we have a question from Teti.
Hello, thank you for the interesting talk. You mentioned that at the beginning that the ultrasonic method that was used to measure the velocity change was thickness insensitive. What type of measurements were you doing?
Yeah, that's a great question. So I didn't know if I was going to have time, so I would excluded the slide. But essentially, we're doing, we have to do 2 consecutive measurements. So since we're in an immersion setup, it facilitates it. But what we have to do is we get a measurement where the wave is propagating through the sample down to an acoustic reflector. And then we take a second measurement that is without the sample in place and going down to the acoustic reflector. So by doing that, we can essentially then just look at the time differences between those 2 sets and eliminate thickness from the equation.
So you have a calibration process for the time of flight that you're doing. So you're doing 2 time of flights, one for the known distance and one for the thickness, the unknown thickness.
Yes, sort of. So it is a consecutive process of 2 measurements, but we don't need, I guess, yeah, we don't need to know any of the distances, is what I want to make sure it's clear. We don't need to precisely measure the distance. What we do need to precisely measure is the temperature in the water, not the temperature, the wave speed in the water, which can be temperature dependent. So in our case, we just put a temperature probe and make sure that that's controlled. But if we have to calculate it, then we just do a Z-scan measurement to obtain that. And that seems to correct for it fine as well.
Okay, thank you.
Yeah.
Do we have any more questions?
There's one in the chat. Yeah.
Oh.
Has the surface roughness between the sample interfaces matter for the acoustic measurement? That's a good question. So for the roughness in general is an important parameter to consider. At the frequencies that we were dealing with relative to the roughness we knew these samples to have, it wasn't a significant factor. So we didn't have to, we started with hand-polished samples. So we weren't dealing with significant porosity, significant roughness. We wanted to eliminate that factor from our analysis. We are actually in the process of figuring out how precisely we can correct for roughness in the type of attenuation measurements that we're doing. So stay tuned for that. And then the second question is, how does the porosity level affect the wave speed and attenuation in terms of the use frequency? That's a great question. So a lot of the figures that I showed you today that had a dependence on grain size, you could almost interchangeably consider some of that dependence with frequency for the polycrystalline models, because the dependence is actually on the product of wave number and grain size. For porosity, it's a little bit more complicated because the scatterers are so sharp. So like the impedance mismatch between the background medium and the pores is large. So it's not as in the wave speed context, it's not as straightforward to determine that relationship. For attenuation, there are some pretty good models on understanding the change in attenuation relative to the frequency used.
And then I've got another question. I really like the section where you were trying to match your data to the pore morphology. See the background, the chart that you used. Where does that come from? Does that come from simulation? Because it was wave speed versus.
Yes. So actually I just stopped sharing, but I'll share again so I can make sure that I'm looking at the right thing relative to what you're asking. So it was in the cold sintering portion, right? So these, these maps, right? So these are actually analytical models. So this Eshelby-Wu model at the bottom, so that Paps and Gregorova paper gives you the effective modulus. So you can get the effective bulk modulus and effective shear modulus as a function of that ratio or of that shape. And then we are just evaluating it for the ranges that we know to be relevant for our case, and then converting those effective moduli to wave speed just using a simple like P wave modulus equation.
No, thank you. And any other questions? Okay, well, if there aren't any more questions, thanks again for an awesome talk. Yeah, and for everybody here, this talk will be on the UKAN YouTube page. So thanks a lot.
Thanks for having
Thank you.
me. Bye.